Good morning students. In previous video we discussed about modern periodic table, that is how many periods present in that periodic table, how many groups present in that periodic table, how many blocks present in that periodic table, who discovered that periodic table. We discussed all these points. Next there are some more topics regarding this chapter, that is among them first one is atomic size or atomic radius. Both are same, atomic size or atomic radius. Here the definition is the distance between nucleus and the electrons present in outermost orbit. The distance between nucleus and the electrons present in outermost orbit is called atomic radius. So that is the definition. I will explain. See, for example, take hydrogen atom. Its electronic configuration is 1s1. So this is nucleus, this is shell. Shell contains what? Electron. This is 1s1. So this is nucleus. From nucleus to this shell, this distance is called atomic size or atomic radius in case of hydrogen. For example, take one more atom, that is lithium. Its electronic configuration is 1s2 2s1. This is the electronic configuration for lithium atom. In this case, two shells are present, 1s and 2s. These are present in two shells. First shell contains 1s, second shell contains 2s. So these are the electrons present in outermost orbit, not these electrons in this case. So the distance between this nucleus to this 2s electron shell is called atomic radius, not this distance, not this distance. Every time we should see what? The distance between nucleus and electrons present in outermost orbit. That distance is called atomic radius. Here also see sodium. Its electron configuration 1s2, 2s2, 2p6, 3s1. 1s2 is present in first shell, we know that. 2s2p, 2s2p, these are present in second shell. 3 is present in third shell. In this case, the distance between this nucleus to 3s shell is called atomic size of sodium. So what is the definition of atomic size? The distance between nucleus and electrons present in outermost orbit. That distance is called atomic size or atomic radius. Here there are some more points regarding this one. See, this hydrogen, lithium, sodium. After sodium, potassium is present. After potassium, rubidium. After rubidium, cesium is present in groups. In first group, after hydrogen, lithium is present. After lithium, sodium is present. After sodium, potassium, rubidium, cesium and francium. All these are present in 1a group elements. See here, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. All those are present in first group. First group, this is group. I told you already in previous video. Vertical columns are called groups, horizontal rows are called periods. So what is the point here? See, here the point is, in case of hydrogen, only one shell is present. This is one shell because 1s1 is the electronic configuration. That means it contains only one shell. Lithium contains two shells because its electronic configuration 1s2 2s1. See, this is one shell, this is one more shell. That means lithium contains two shells. Sodium contains three shells because its electronic configuration 1s2, 2s2, 2p6, 3s1. So it contains 1, 2, 3. Similarly, potassium contains four shells because its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That means it contains four shells. Similarly, it contains 5. It contains 6. What are these? What are these? 1, 2, 3, 4, 5, 6. What are these? These are shells. That means hydrogen contains one shell. That is this shell. Lithium contains two shells. That is these two. Sodium contains 3 shells. 1, 2, 3. That means based on electronic configuration we can say that how many number of shells present in respective atom. So the point is, see, from hydrogen to lithium shell number increases. From lithium to sodium also shell number increases. From sodium to potassium also shell number increases. From potassium to rubidium also shell number. That means in groups from top to bottom. This is important point. In groups from top to bottom, atomic size increases or atomic radius increases due to increasing number of shells. This is very, very important point. I repeat once again. In groups from top to bottom, atomic radius increases due to increasing number of shells. Next, this is happen not only in this group, it is happening in all 18 groups, not only one A group or one group. This property repeats entire groups, all groups. That means in any group atomic radius increases from top to bottom due to increasing number of shells. This is very, very important point. This point comes in again 11th class and again in 12th class. Next, now we see in periods. See, I take some elements in periods: boron, carbon, nitrogen, oxygen. See here, boron, carbon, nitrogen, oxygen, fluorine, neon. I take just a few elements. Its electronic configuration 1s2, 2s2, 2p1. Its electronic configuration 1s2, 2s2, 2p2. Its electronic configuration 1s2, 2s2, 2p3. Its electronic configuration 1s2, 2s2, 2p4. We know all these elements present in same shell, all these elements present in same period. All these elements, see, boron, carbon, nitrogen, oxygen, fluorine, neon, all these are present in same period, second period. So the point here is what we are discussing about, what? Atomic radius. See, if you see this one, electronic configuration 1s, 2s, 1s, 2s, 2p, 1s, 2s, 2p, 1s, 2s, 2p, 1s, 2s, 2p, 1s, 2s, 2p. That means what? All contains two shells. 1s contains first shell, 2s, 2p contains second shell. That means this boron contains two shells. Similarly, carbon also contains two shells, 1 and 2. Similarly, nitrogen also contains two shells, 1, 2. Similarly, oxygen also contains two shells. So in periods, shell number is same. There is no chance of increasing shell number. I repeat once again. In periods, shell number is same. There is no chance of increasing shell number. But what about its atomic size? Whether atomic size increases or decreases? That is the point here. So the point is what here? In all cases, number of electrons increases. See here, 2s to 2p1. Here 2s to 2p2, 2s to 2p3, 2s to 2p4. That means number of electrons increases. When we draw the atomic structure, see, this is nucleus. This is first shell, 1s2. This is second shell, 2s2, 2p1. In case of boron. In case of carbon also same, two shells, first shell, second shell. Here also same. What is the difference? Just number of electrons difference, 2s to 2p2. But shell number is same. Here 1, 2. Here also 1, 2. Shells number same. So the point is what? If number of electrons increase in same shell, that is the point. Here second shell contains 3 electrons. Here second shell contains 4 electrons. In case of carbon. In case of nitrogen, 1s2, 2s2, 2p3. This is nitrogen. That means in nitrogen, second shell contains 5 electrons. Here 3 electrons, second shell, this is second shell. This is first shell, this is second shell. So here 3 electrons present in second shell, here 4 electrons present in second shell, here 5 electrons present in second shell. So the point here is what? If number of electrons increases in same shell, if number of electrons present in same shell, then the attraction between nucleus and that electrons increases. That is the important point. I repeat once again, this is very important point. If number of electrons increases in same shell, then the attraction between nucleus and electrons increases. Here 3 electrons present in outermost orbit, here 4 electrons are present. So compared to here attraction is more between electrons and the nucleus. Here 5 electrons are present, so that the attractions between these 5 electrons and the nucleus is very more compared to here. So the point is what? If number of electrons increases in same shell, then nuclear attraction, that means attraction between nucleus and electrons increases. If nuclear attraction increases, then these shells comes close towards nucleus. I repeat once again, if nuclear attraction increases, then these shells comes close towards nucleus. If these shells comes towards nucleus, then atomic size decreases. So the point is what? In periods from left to right, the atomic size decreases. Because nuclear attraction increases. Why nuclear attraction increases? Because electrons and the number of electrons increases in same shell. If number of electrons increases in same shell, then nuclear attraction increases. If nuclear attraction increases, then those shells comes towards nucleus, then automatically atomic size decreases. So what is the point here? In periods from left to right, in periods, not only in this period, in all periods from left to right, atomic size decreases due to nuclear attraction increases. I repeat once again, in periods from left to right, atomic radius decreases due to nuclear attraction increases. In any group from top to bottom, atomic radius increases due to number of shells increases. In any period from left to right, that means from here to here, not from here to here, from left to right, atomic radius decreases. That means boron is more atomic radius compared to carbon. Carbon is more atomic radius compared to nitrogen. Nitrogen is more atomic radius compared to oxygen. So from left to right, atomic radius decreases due to nuclear attraction increases. So in this video I discussed 3 points only. One is the definition of atomic radius. Second one is how it varies in groups and how it varies in periods. So only 3 points. These 3 points: atomic radius definition, variation of atomic radius in groups, variation of atomic radius in periods. These 3 points are very, very important. We will discuss some more points regarding this chapter in next video. Thank you.